lecture of CSE141. So today we are going to have a complete review on the final. And well, if you attend the lecture today, I will make sure that I cover all the important aspects that you need to know for the final exam and give you some hints regarding some question that need to think a while. But you know, the most important thing that I want to say is that regarding the final exam, all you need to know, it's an accumulative exam. So in this way, you have to have a complete picture about computer architecture to ace in the final. So regarding the complete picture, what's a complete picture? So the complete picture of computer architecture is that you need to recognize that all the computers we have right now is a von Neumann computer. So by von Neumann computer, we mean it means that your computer has processor and memory as the main part for executing your program. But as long as we always want our program, compiled program, and the data to be stored persistently, so you can never imagine that a von Neumann machine without a persistent storage. So that's why I always incorporate the storage in this picture, although we didn't spend too much time talking about storage in the class. And for the von Neumann architecture, if you want to execute a program, the very first thing you have to do is to load your instruction and data into your memory. So everything that you need for your program has to present in a memory first, no matter where they were. And your processor will fetch instructions also from the memory. So every time when I ask you about, well, consider the memory, the memory is not perfect and your cache may miss, then what's the average CPI? A lot of you forget that 100% of the time, your instruction needs to access the memory because the instructions itself would also need to be coming from the memory, right? And not just the data, right? So data, occasionally you like maybe 30%, 40% of the time, your instruction will need to access data. But don't forget that except for data, every instruction also comes from the memory, right? And by loading different programs into the memory, your computer can perform differently. So that's the whole idea of von Neumann architecture. And to execute an instruction, you have to go through instruction fetch, decode, execution stage, and memory, and write back. And you also need to maintain the PC correctly if there is a branch. If the branch is taken, so it will be the target address. Otherwise, it should be PC plus 4. And because your computer, your processor executes a program looks like this. So depending on how many of the instruction that you need and how long is it to take to execute each instruction, your performance equation will be a combination of the instructions per program, cycles per instruction, and the cycle time. So, and our definition of performance is always the reverse of execution time. It means that the longer the execution time, the worse the performance. And regarding the execution time equation, the cycle time is always the reverse of your frequency, and we usually use the frequency to represent the capability of processors in executing instructions. The quick conversion of that is like 1 gigahertz is typical is 1 nanoseconds. And another thing that we learned regarding performance evaluation is MDOS law. And MDOS law is nothing too different from the definition of speed up. So that's not too different definition from the speed up, which is the baseline execution time over the enhanced execution time. However, the form of MDOS law does give us some convenience in calculating the speed up without giving you the full picture of what's going on in the whole program. And regarding the, and then we talk about the pipeline processor, and you can consider, well, since we learned like advanced the pipeline design, you can consider this kind of processor as a single issue pipeline processor with only one fetch width, only one issue width, right? So that's what we learned. And the purpose of having the pipeline processor is to execute instructions. And one of the biggest thing that I think a lot of you, I saw a lot of your posts on Piazza, a lot of you still have struggling with why there's a data dependency, why there's not data dependency, is because you didn't spend sufficient amount of time to figure out what to do in what each instruction is exactly doing. And one thing that I think the biggest confusion here is that for store instruction, some of you are still confused about why both of them are sources, as we said, right? The S1 is the value you want to store into a memory address. And S2 is like a pointer, help you to calculate the effective address. So you are not storing into S2. S2 is just a pointer. So you are storing to where S2 is pointing to. So that's why S1, S2, they are both sources. And same thing for branch instruction. You compare on S1 and S2. So both of them are inputs. None of them would be the output. So this is one of the biggest confusion that I saw in your questions. And for we say for the pipeline processor, we have hazards, and to resolve the control hazard, we learn branch prediction, and there are better branch prediction, better ways to do branch predictions, right? And those are, and because you have branch prediction, so and also because so we will see that. Because of a branch, so like for these pieces of code, C and D, they perform better because you are reducing the number of branches. So to avoid the overhead of misprediction, even though and for C and D, because they also have the effect of loop unrolling, so you can reduce the number of instructions at the end, right? So that's what we end up with. However, one of the questions that you probably didn't erase, but after I show up this picture, and that's what we start to talk about after the midterm, is that the memory, right? So the processor and the memory, they have a huge performance gap. So if that's true, then C and D, they basically try to use a lookup table to reduce the amount of instruction they need. So it turns out that if the memory is so slow, then it's impossible for C and D to outperform B and A. So it's really important that there must be something that we have been done in the computer architecture to make memory great again. And that thing is called memory hierarchy. And the basic idea of memory hierarchy is instead of just having your processor directly interact with that slow DRAM, we start to put a little bit of more expensive but very fast SRAM in between your processor core and the DRAM. And we also learned that if you make this layer, if you make this multi-layer, then potentially, although each lower level in the memory hierarchy is going to be slower, however, the manufacturer cost of slower memory is always cheaper than the manufacturing cost of the faster memory. So you can gradually you can still improve performance, but at least it's better than like having everything going to the DRAM if your L1 cache is a mess. So that's the benefit of building hierarchical memory, and that's where we are living right now. So previously we have been talking about if you don't have the cache, then you have everything directly go. You have 100% of the time your instruction needs to access the memory, and 30% of the time your data needs to access the memory as well. So you will end up with an average CPI of 69. However, if you have a memory hierarchy to help you, like this example, you have 2 levels of the memory hierarchy, then you can bring the CPI down to just about 5, right? However, you might be curious about like, okay, why adding a small cache would help? And the answer is that because we have locality. So most of the time, your application only work on very small pieces of code and data. So think about spatial locality. If you are not interfacing any branch, then by default, you are moving just to the next instruction. And for data, if you have your data structure like an array, then most of the time you are moving to the next. So let's look at so that's spatial locality, right? So another thing that you might get implication from here is that, okay, if I am implementing a data structure like linked list, and linked list most of the time you are going to access the random memory locations. So if your data structure is designed to be a linked list, you won't be able to get the benefit of spatial locality. So linked list is slow, not just for the fact that you have pointer dereferencing in your data structure, but also the fact that you cannot fully utilize the benefit that the cache would help you capture the spatial locality. So linked list is terrible in terms of performance. So however, array, if you can use an array, then it will help your code exploit spatial locality better. For temporal locality, it means that your application will revisit the same thing again and again. A good example in your code is branch. So if you have a branch and if you have a loop, then most of the time you are going back to the same instruction again and again. So that's temporal locality. And for data, like a lot of the algorithms, they have the lookup table, they have to update a table. So those tables, they will be revisited several times. So that's temporal locality. So, but the truth is that the truth is that as long as you could create a data structure, hardware data structure to capture the most frequently used data or data nearby, then you can have your application running efficiently, even though your cache is not as big as your data, the whole data set. But how this structure is designed? So the basic idea of the hardware structure of your cache looks like this. So first of all, you organize your data into blocks. And these blocks, they store consecutive data elements. So as you can imagine, every time when you have something missing, saying that if I am requesting JJ, then it's very likely that when you have a miss, then something else nearby will also be brought in because it's every time when your cache needs to bring in or kick out data is all on the granularity of a block. And block means that I am going to store consecutive data elements within a cache. So so in this way, the cache can help us to exploit the spatial locality as we just mentioned. So some of you asked the question, like, okay, if I have an element missing in an array, say A0, why the next time when I revisit A1, when A1 is not in a cache, is not a compulsory miss, but a conflict miss? The answer is because very likely when your A0 is a miss, we already brought A1 also in a cache blocks, because remember that cache block usually is like tens of bytes, and your data structure or say a primitive data types is only single digit of bytes. So that's why typically every time when you have a miss on an element, you're going to bring nearby elements, because it's very rare the case that your single element is going to occupy for the whole block. So here's the basic idea of block. But the more complicated thing is that, okay, how do I know if the those blocks that I have in a cache are those stuff that I am looking for? So you need text to attach to each block, and a tag is basically the upper bits of your or say the common parts of data in your of the data block, or say the addresses in your data block. So there in a cache, we also have a valid bit. So in the last lecture, you also learned that if there's a coherence miss, then I will probably invalidate the data, meaning that the data here is not trustworthy. And there's also a dirty bit, meaning that my data has been polluted or say has been modified. So I am the only one who has the content. Oh, Nick, question?
Yes, I never really learned this, but how do you represent the size of data in one block?
What do you mean by represent the size of data?
Like, how would you
calculate?
Like,
well, so that's why we have the equation called C equal to ABS, right? And the B means the block size, right?
Oh, okay. So if I were to look at
block size means that how many bytes of data can you accommodate in a single block?
Oh, okay. I see. Thank you.
Yeah. Okay. So so right now, given that cache is organized as a block, each block contains a valid bit, a dirty bit, a tag, and the valid bit, dirty bit, or the tag, because they are not the data, so they are considered as overhead. And but how can we? But in addition to that, because if you do not organize your cache blocks carefully, you have to perform a linear search. So to reduce the search time of block, we organize those cache blocks into sets. So a set would contain multiple blocks that will be accessed concurrently when a cache access is performed. So, and typically we said this is a two-way set associativity cache if there are two blocks within the same set. So this graph demonstrates a two-way set associativity cache. So with this idea, when you want to access the cache, first of all, you have a block offset. And for this example, because I have 16 bytes in a block, so you need 4 bits to represent the data you are requesting is within which byte within this block. And use that information. Your cache can select, use the mux to select the right word to output. In addition, part of your memory address bits will be used as the set index. So you can consider this index as a hash output of your memory address. And use that hash index, you will know which set in the cache do you have to look up. And the remaining bits, they are the common prefix of your data blocks, so they are considered as tag. So for this example, we know the set index after partition is 0, 1, 0. So we will go to the second set. And in the meantime, you can use the block offset like this example. It says I am accessing 100. So that's the fourth word in the cache block, the fourth byte in the cache block. So I can use that as the blue part pointed out. That's what the mux will select. And use the red stripe, meaning that I am accessing a second set. And the remaining part will be the tag comparison, and my tag here is 0x10. So if you look at the tag, the left-hand side actually it matches the tag that we are accessing, so it's a hit. And when we output, we just select the left-hand side as our output. However, if nothing has been found, it's called a miss. So that's a basic idea of accessing the cache. And remember, every time we access, it's on a block basis. So when you read data, first of all, you issue a load request from your processor, and if it's the cache would partition the address as we show here into tag, index, and offset. And if after the process of searching the cache, we found it's a hit, we will directly return your data to the processor. Otherwise, you will have to accommodate a block. Again, it's all on a block basis, a block that contains the data that you are looking for. And to make the space for the incoming block, sometimes you have to kick out a block. And the policy of kicking out a block is the LRU, list recently used. So in this way, we can exploit the temporal locality. So when we kick out a block, and if the block is a dirty block, and it means that you are the only one that has the right content, and if you don't back it up somewhere, you are going to miss that data permanently. So in this way, you have to write back first and try to fetch the block after you finish the write back. However, there's also a potential that the next level cache doesn't know. So you have to go to the next level memory hierarchy and again, write back first and fetch the block. And once you have the block ready, just return it and all the way back to the first level memory hierarchy. So that's the process of accessing your data when it's a read. And for write, it's nothing too different except for the fact that when you perform the write, you have to set the 30-bit. So we know the stuff that you are accessing has been modified, and the rest of the process is the same. So how to evaluate the cache performance? A lot of you would like to memorize this this equation and try to ask, okay, what H is representing for that. However, what I really want you guys to do is that draw draw a picture like this, and it's clearly that you know what to do. So for example, like this one, if first of all, I want to perform an access, right? And if it's an instruction, every instruction has to perform this part, right? So you know this pass is 100% of time. And when you try to access the instruction memory, as the question mentioned here, miss rate is 5%, and hit time 1 cycle. And when we say 1 cycle, you can assume it's aligned with your processor pipeline. So there's no additional overhead. But however, if it's a miss, then you have to go to the next level memory hierarchy. And as we draw here, you are draining the whole block, meaning that you are draining data with offset from 0 to b minus 1, making them into part of your L1 cache. And within this 5% of miss, there is also 10% of the time, 20% of the time you will have another miss, right? So 20% of the time you will have to go to DRAM. However, as we mentioned, there's 10% of the case, there will be a dirty. So you are going to have, for this 10%, in addition to the 100% of the time you are going to fetch the block, you have to have additional 10% rights to, or say 10% access to the DRAM. So that's why if you look at the formula that we put here, right? This 1 is the base CPI. This 100% means that every instruction. This 5% means the miss rate, and this 10 means the hit time of L2. And this 20% means 20% of time is still a miss. And this 1 means that everyone needs to fetch the data. And this 10% means that 10% of them are dirty, and 100 means 100 cycles delay, right? So that's why this come up with that. And for the data access, go through a similar path. You will derive another part of the equation like that, and this would give you the answer that we finally got, right? So for this question, if possible, try to make your equation as clear as possible so we know what each number is about, because you can put random numbers there and potentially you can well, there's very low chances, but sometimes you can get the right answer, right? But if you can, but it's more of a case that you put the right number in, but you know, our fingers didn't put the numbers in the calculator correctly, so we got wrong numbers. So if you don't have a format of the right equation, we cannot give you any grades if your answer is wrong. And it's very difficult for the TA to figure out what each number is representing. I mean, I always receive students arguing that, yeah, you can clearly tell like 10% here means what, right? But if you look about like this question, I have 2 parts of the 10%. Which 10% are you referring to, right? And nobody can guess what you would like what you are thinking about at that moment. So don't. So if you really want to avoid the confusion when we are grading, try to put it as detailed as possible. Label your numbers and put everything on the equation. Those are all possible. The only thing is that thinking about that, well, treat me or the TA like an idiot, right? We know nothing about us. We are robots. We are robots. So we have no machine. We have no intelligence. So just let us know what each number is about, and in this way we can give you grades, right? So that's the performance evaluation. And now another thing is that, okay, Professor, I understand what you're talking about. We have to partition addresses into tag, index, and offset. But how many bits are there in the tag? How many bits are there in the index? How many bits are there in the offset? How do I know? So here is the equation C equal to ABS, where C represents the capacity. A represent the way-associativities, means that how many blocks are there within a set. And for the spatial configuration, like 1 is for the red map cache. And for block size, it means that how many bytes are there in a block. And remember, every time when you miss, you are fetching consecutive blocks that's starting with offset 0 to offset b minus 1. And number of sets means that how many sets are there in your cache. And and if you have a fully associative cache, which I never talk about in a class in detail, you should use 1, but somewhere you will use that. When we talk about the memory DRAM, you will have a feeling like what's going on as a fully associated cache. But give you an example like this. If I give you an AMD Phenom 2 processor, which is a processor about like 10 years ago, and you C equal to ADS, it's not too difficult for you to figure out that, oh, because it has 512 sets. And remember, index is what we use to identify the sets. So the index is related to the number of sets you have and log it, and that will be 9 bits. And the offset is used to identify which byte do you have in a block. So you have to use log block size to get your offset bit. And because when we say 64-bit memory address, it means that your memory address is 64-bit wide. So the remaining bits will be the tag. So that's how you derive these numbers for your Phenom 2. And for Intel Core i7 does the same. And index offset, they are 6 bits, tag, they are 52 bits. And you might ask me like, okay, why do I need to know this? And the reason is because in many of the cases, before we run a program, we want to analyze if this program is going to be efficient on the real processor. So you have to evaluate and simulate if this is possible. So here I give you an example where if you use C equal to ABS, you will know that it has 3 bits for index and 4 bits for byte offset. So when you want to solve this kind of cache simulation problem, the very first thing that you have to do is that I have to list at least part of the sequence of the memory addresses, and then you C equal to ABS to partition the address into tag, index, and offset, and then you can start simulate the behavior of your cache. So for this example, in the first x-axis, the index is 0 and the tag is 100. However, there's currently nothing in the cache, so we know it's a mess. And now the second run, because now in index 0, there is something called 100, so we know it's a hit. And again, for this one, 001 doesn't have anything, so we have to bring a block called 100 here. However, because the first time we have that, there's no block there, so it's a mess. But the next time, because 100 block is right there, so it's a hit. And however, this time, when we go to index 1, although there are something called 100 here, but what we are looking for is 110. So it's still a miss. And in the meantime, don't forget to bring in 110 into your cache. And if you keep iterating, you will figure out that the rest of them are hits. And so given that you know the number of bits in each field of the AMD Phenom 2 processor, again, just do the same thing, right? The first part of this piece of code is to load A0, and this is the address of A0, and partition them into tag, index, and offset. And you will figure out that the tag is 4, index is 0. Currently nothing here, so it's a mess. And then the next address is 30,000 in hex, and partition them, figure out that the tag is 6 and index is still 0. However, remember, this is a two-way set associativity cache, and currently we can still have one more block into index 0. Then, but because there's no 6 in the past, so it's still a mess. Now, let's go to the next address and partition it. Its tag is 2. However, it also mapped to index 0, and we have only 2 ways. So you have to pick someone from 4 and 6 to kick out. And because we want to explore temporal locality, so we want to keep the stuff that we accessed recently in a cache. So we kick out the 4th one. So turns out that when you serve this miss, you have to evict 0x4. And now you have 6 and 2 in your cache, index 0. And go back to this address. Aha. This is tag 4, index 0. And tag 4 previously were there. So you have to, it's a miss and evict 06. And it's continuously going to be a miss. And this miss is the rest of the miss is going to be a conflict miss because all of them has been in the cache before, but it's just because every time when you have another miss, you just kick it out. However, for 16, it's another sequence of miss, and it's compulsory miss because, as you can see, this is the index 1. This combination of index 1 and tag 4 we have never seen this before, so it's a compulsory miss. However, for this piece of code, if you analyze it before, you will figure out it's 100% miss rate. So if you are a very careful programmer, you should never write this piece of code on this processor. However, if you have an Intel processor, it's very safe to write this because when you go through the third address, because we have 8-way in Intel Core i7 processor, so the same index can accommodate 8 different blocks. So although this is a miss, but nobody get evicted, so the rest of them would be a hit, and the hit rate of this piece of code is like 93.75%. So most of the time you are going to have a hit. However, for the AMD processor, everything is going to be a mess. So this piece of the code works well on Intel processor, but doesn't work well on the AMD processor. So how to optimize your code or your hardware architecture for the memory performance is very important for you to figure out the cause of memory misses. Cache misses. So compulsory miss means that the first time miss, and the capacity means that, so if you have a block that, and again, first access to a block. So even though I am not accessing A1, for example, however, because another memory access, so for example, like A0, brought A1 in the cache. So A1 has been in the cache before. We didn't use it, that's fine. However, if it has been presented before, then it's not going to be a compulsory miss. However, it will be a conflict miss because the data has been replaced by another block. And that's why A1 in the previous cache, in the previous case, it's called conflict miss in the AMD example. And capacity means that no matter how you change your way-associativity, like I just make the data can go anywhere in a cache, there's no restriction code set, it's still going to be a miss, then that's called capacity miss. So look at the simulation, right? So if I do a direct map cache, you will figure out that, well, in addition to compulsory miss, when I access this block, this cache address, well, you will see 0, 1, index 1 and 1, 0, they were here before, right? It's just because they have been kicked out because of that. So there is a conflict miss, right? However, if you want to avoid this conflict miss and use our two-way cache, two-way set associativity cache, you'll figure out this is gone. So so that's a conflict miss. On the other hand, if you can increase your way associativity to eliminate that miss is not a capacity miss. So how to distinguish capacity miss and conflict miss is that try to increase the number of ways as much as possible. And if it's still a miss, then it's a capacity miss. So for the AMD Phenom 2 processor, if you go through this example, except for the initial access of 0 index, everything between 1 and 15 would be a conflict miss because of that. Okay, so for Intel processors, we don't see conflict misses because we are having sufficient amount of ways in our cache so that you can avoid those conflict misses. So in your homework, we have been talking about matrix transpose, and this is a giant example. I wanted to go practice at home because this is really useful. And if you can solve this question, then I believe you are probably very good about like what happening in the cache. So for this question, again, right, we have, as I said, if you want to solve this question, you have to show the sequence of memory accesses, right? So if you look at these pieces of code, you are going to access A and B, right? And you are definitely going to load A first and store to B. So what's the access of sequence of, and they are accessing interleavingly. So what's the access sequence of A looks like is determined by J times N plus I. right? So when your j and I are both equal to 0, you are going to access A0. However, if because n equal to 128, so when I increment j, you are going to 128 and 256. And then you go to the maximum value you are going to reach when I equal to 0 would be 127 times 128. And then you start with another run, A1, A129, and A127 times 128. And they are going to interleave the access with B. And for B, it's very regular, B 1, 2, 3, 4, 5, 6, 7, like strictly incremental, right? So if the cache is a 64 kilobyte size, two-way 64 byte block, each block can hold, and for this example, I use double, and double is 8 byte. So each block can hold A0 to A7 or 8A to A15, A16 to A23. Don't ask me why there's only A, because this is double 8 byte and you have 64 byte block, right? And for B, the same, right? So for the first time you access an element in a block, it will incur a compulsory miss for sure. And since we are traversing all the elements within this two arrays, so depending on how many elements that you are accessing divided by the number of total blocks that you have to access, that's the number of compulsory misses. So you have this piece of code go through every element, and compulsory misses occurs every 8 elements. So you have a total of 128 times 128. That's the size of the data structure, and divided by 8, because when you hit the boundary of 8, you are going to have a compulsory misses for the first time access of a new block. And it's always, it will happen, right? So every time when you go to the, and there are 2K times of the first time visit for array A, and the same thing for 2K times first visit of a block in array B. So this is the total amount of compulsory misses you have. And the rest of them would be conflict misses. So how to tell if it's how often this conflict misses occurs? You really need to simulate a cache. So look at so you have to list the address like this again, and for this time, well, you always know that, well, for A0 it's going to be a compulsory miss, and now you go to A128 first, is also a compulsory miss because this is the first time you exit the cache. Yes, Harry's question.
This is question number 2 on assignment 4, correct?
This is a question. This is maybe a similar to the question number 2 on assignment 4.
Okay.
Yeah. Okay. So so now the index 1, 0, and 4. This is the first time we saw it. So that's a compulsory miss. So if you think about that, right? If you go through the first run, so when j equal to 0, right? All the first run of this A blocks, they are going to be compulsory misses. And when you go to like 4K, right? It's still going to be a compulsory misses. However, when you go to the 4K, we are seeing the index has been reused. And given that you only have 2-way, so it's very likely you may have to evict someone within the same index, right? So the pattern here is that every 4K, you might have to evict someone. So the next time when you visit load A1, right? Like A1. So this is tag 4, index 0, right? It's very unlikely that you are going to keep 0, 4 in your cache, because in the middle, there are so many of them have been trying to compete for index 0, and you are further away from being accessed. So very unlikely A1 will remain in your cache. So this is a conflict miss because you have been evicted in the past, right? And again, when you are accessing A1, you have to kick out somebody else to accommodate your block. So this, you can imagine that whenever you access A, it's always going to be a miss. And except for the first element within a block, everyone else is going to be a conflict mess, right? And however, for B, right, if you look at B, right, your B access is very sequential, right? And even though you are sharing the index with A, however, because the B is updated frequently, so according to the least, the recently used policy, it will always be kept in a cache. So B will never miss due to conflict. The only type of miss that you will see in B will be compulsory misses, because once the block is fetched, it will be used until everything be retired, or everything doesn't need to be used anymore, right, in these pieces of code. So you can imagine for A, everything is a miss. For B, only compulsory misses. So that's how we got the final result for this matrix transpose question. So how to improve 3Cs? And we already learned that you can change your cache configuration, like conflict miss, just make the way-associativity higher. Compulsory miss is related to how many stuff you bring in the cache every time. And capacity miss is called capacity miss because your capacity is not enough. However, it's also important as a software programmer, you know what kind of data structure can make your performance better. And for this example, because if you make object of arrays, when you access it's better, it's easier for your code to exploit a sequential locality, so your performance will be better. And it also explains why in databases we see column store more often than row store, because for column store, most of the time, think about your SQL. You are selecting a column and you are selecting columns, and then when you judge like the where condition, it's where some value within a column, right? So column store is going to help you better exploit the spatial locality. So sometimes, right, if you are a good programmer, you can also change the pattern. So like this example, I split the original loop into two. So even though it's a two-way set associativity cache, you will see the data cache miss rate will be as low as Intel processor. Matrix multiplication is a very important algorithm that's used by machine learning nowadays, especially deep learning, right? And if you just write naive matrix multiplication, then it doesn't scale as the algorithm suggested. So, and the reason is because each row is big enough to occupy half of the cache. And your cache, like Intel Core i7 processor, only has 32 kilobyte cache. So no matter how you increase your way-associativity, because each row is this big, and you have to store 2 rows and 1 column for ABC. So it's impossible for you to accommodate everything. So there's going to be capacity miss all the time. So what you will do to improve this piece of code, and what we suggested, is the block algorithm. So every time you only perform the matrix multiplication on a sub-block basis. So I partition the block into sub-block, and I just need to calculate the partial sum of each subblock. And when I visit another subblock, I will aggregate the sum to the subblock again. But in this way, at least every time when I calculate this subblock, the size of data that I have to cache will not exceed the capacity of my cache. So in this way, I can remove the capacity misses significantly. So that's why the block algorithm is useful. And in fact, that's still the most useful algorithm in matrix multiplication. So a lot of you, if you read the algorithm book, it tells you that there are some algorithms can shrink the complexity of your matrix multiplication from n cubic to n 2.4. However, if you check the Wikipedia carefully, they will tell you that's impossible to implement because of the huge constant, right? So block algorithm is by far the most effective algorithm in implementing matrix multiplication on CPU. And here is a summary of optimizations, and we will going to have question asking you about optimizations of code. So make sure that you remember those. And virtual memory is another concept that we introduced. And again, there are many abstractions in our system. And whenever your system interfaces a problem that we cannot address, we would add another layer of abstraction. So virtual memory is one of the abstractions. So the basic idea of virtual memory is that we make the instruction and the data to live on a virtual memory space, and the virtual memory abstraction would dynamically map a page, a memory page into a physical memory page. And whenever you access the data, because it's a virtual memory, so the virtual memory abstraction will have to translate the address into the right location. So, and the current algorithm mechanism is called demand paging. So whenever you need a page, we dynamically load it into the memory. And whenever the physical memory is running out of space, we have to kick out a page and put the desired page into the memory. So that in that way, you will have a feeling this virtual memory abstraction makes the physical memory, or say your DRAM, as a cache of the virtual memory. So, and an analogy of that is that the virtual memory treats a memory page like a block in a cache. And because your data can go anywhere in your memory, so it's like a fully associativity cache. And there's no take array available for the DRAM because that's a software abstraction. However, we do build a software data structure called page table to mimic the behavior of tag arrays in a virtual memory abstraction. So whenever you are accessing a memory address, you use the page table to tell you which physical page may contain your data, and you use the page offset to output your data. And because of that, so even though two programs, they have the same virtual address, but because their translation is done by different page tables, so they can point out to different address. And the basic idea of translation, as I mentioned, is that the page is like a block in your cache. So depending on how many bits, how big is your page, how many, there will be corresponding numbers of bits that you need for your page offset. And because it's just an offset, so it doesn't change before and after translation. And you will use the virtual page number being translated to get your physical page number. So the size of page table is usually very big if you don't optimize it. So our current architecture plus together with the operating system decided to make them like a beach plus tree in a way that we don't create entries unless this part of the tree is used. So in this way, we can shrink the size of the page table. However, it also create a case that whenever you need to access the page table, you have to have additional numbers of memory accesses because your page table resides in a main memory, and every time you want to access the tree, you have to access the main memory again. So as you can imagine, like a memory move instruction in x86 will cost at least 10 memory accesses. So that's very inefficient. So in architecture, we invented something called TLB, translation look aside buffer, which is a small dedicated cache just for storing the entries of your mapping table from your page table as a cache. And then in this, however, the previous method that puts the TLB in between your processor and L1 is inefficient because it's in a critical path. And this method of parallel access, but allowing your L1 cache to use virtual address will be problematic, as I just showed you, because there are programs using the same virtual addresses. And from that, you cannot tell. So what you really need is that I need to be able to distinguish physical accesses to see if it's a hit or a miss. So the basic idea right now has been widely implemented in our hardware. It's called virtually indexed physically tagged cache. So it utilizes the fact that the page offset would never get changed before and after translation. So we make the set index and block offset part of the within the page offset. So whenever you access the cache, you can still use the virtual memory address as the input, since the set index and the block offset, they are going to be the same. But in a tag array, you store the physical address tag. So whenever your TLB lookup is finished, you can still compare the physical address tags that you store in the cache. So the process of doing this is like this. So first of all, you still partition your address, and don't forget the set index and block offset. They are coming from your virtual address in the very beginning. And the remaining part would be the virtual page number, or say a virtual tag. However, you don't use that as comparison. Instead, you only use the block offset and set index to access your cache, and you use the lookup result from your physical page of TLB to see if the physical page number really fits my tag area in my cache. And if that's a match, then that's a hit. Otherwise, it's going to be a mess. However, as you could imagine, because you have to make sure that your set index and block offset completely fit within your page offset, so it puts some constraint in your cache configuration. And if you remember C equal to ABS, it's not too difficult for you to figure out that if you only have a direct map cache, your cache capacity can only be 4 kilobytes if you want to select virtually indexed physically cache. Okay, so after talking about the memory, we say we want to make the execution of your program more efficient. And you also know that, well, sometimes because you have memory, you have cache misses, so your instruction can take surprisingly long time. So we want to have the capability to dynamically reorder execution of your instruction to fill in the slots whenever a long latency instruction is occurred. So if you look at the tips of drawing pipeline diagram previously we showed in a class is that if you want an instruction to be executed, in theory, these are all the 3 things that you need to know. No other instruction is using my functional unit. The instruction has completed its own work, and the next stage, it has all its inputs ready. So if we say if the instruction is ready to execute, meaning that the instruction is ready to move from instruction decode stage to execute stage, all you need is these 3. Whenever the instruction is decoded, whenever the inputs are ready, and whenever the target functional unit is available. So with that, all you need to, as you can imagine, the most important thing is that when the inputs are ready. And so when you schedule an instruction, what you really need to see is the data dependency graph. So for these pieces of instruction, to draw a data dependency graph, just put an arrow whenever there is a dependency. And for these pieces of code, you will figure out that if you draw the data dependency graph, there are actually 2 separate dependency chains. So when you execute 1, 2, 3, and 4 to 10, they can actually be decoupled. However, right now we are not able to execute 1 and 4 together. It's just because we have false dependencies where we have 2 types of false dependency right after read, meaning that if you try to reorder the later instruction, then it will overwrite the source of an earlier one. So 4 and 1, they are in this category. They are also right after write. So even though 6 and 1, they have no data dependency at all. However, if you try to reschedule 6 before 1, you are going to mess up the output of 1, and everyone depends on 1 will not be able to get its right result. However, if you can rename your registers, then this dependency will be completely gone. So the basic idea of eliminating false dependencies is register renaming. And we provide a set of physical registers and a mapping table to map architectural registers to physical register. And whenever you have a new output, you give it a new physical register. Like what we did here, whenever you have a new output, just rename it to the new output. And in this way, you can eliminate all the false dependencies. And so this is the revised pipeline. And as you learned, it's very similar to the pipeline of modern processors. And in this class, we will never ask you to draw a register renaming pipeline like this. All we want you to know is that the capability of issuing instructions, because thinking about that, right? The capability of issuing instructions means the capability of how you can execute instructions. So using this is already very representative for your performance, and there's no need for you to finish the rest of the pipeline because this is complete. This already shows the performance that you can get. So for this example, if you can arrange your data flow graph carefully by making your arrows aligned with the latencies that you need for each instruction, it's not too difficult for you to figure out how many cycles it needs to empty your issue queue. And in addition to that, right, we also try to, as we said, right, the capability of how you can fill your pipeline decides the capability how your processor can affect performance. So we have superscalar processors that will be able to fetch and decode more instructions than just one, so that we can completely fill the pipelines we have. So in this way, in superscalar processors, there are going to be two terms. The issue width means that how many pipelines do we have in the processor? And the fetch width means how many instructions can the processor fetch and decode at each cycle. So you can imagine your processor has a front end and a back end, and the fetch width is the capability of the front end, and the issue width is the capability of your back end. So that's the distinction between fetch width and the issue width. And so with register renaming, if you have two-way superscalar, as you can see, if you draw the data flow diagram or use the pipeline, you know you only need fewer cycles. However, even though I give you unlimited fetch width, unlimited issue width, there are still code like linked lists perform terribly. So for this piece of code, another solution is that since we cannot fully utilize our processor pipeline from this kind of program that sucks, what if we use simultaneous multi-threading, which try to grab instructions from different threads to fill in the pipeline same time? So one thing you have to remember is that simultaneous multi-threading allowing the processor to fill in its pipeline by using instructions from other threads, other processes. However, it also means that you have to share your resource with others. So most of the time, you are going to see a performance degradation of a process or a thread. However, the overall throughput is going to be improved. And if you can make your program parallel, you can still get performance benefit because right now you are making parallel threads for an application. However, without modifying your program, there's no way a single program can get benefit from simultaneous multi-threading. So when we talk about the architectural design right now, is highly impacted by the power and energy consumption. And the power means the instant amount of electricity has been drained to make this action for your circuit. So it's an instant time. And for energy, it's a period time. It's a total period of power has been consumed. So for battery life, it has more of related to the energy. However, for heat, it's more related to power. So for power, there are two types of power: dynamic power, which is a cubical relationship with your frequency. And so most of the time right now, we are not aiming at doubling your clock rate because it gives you probably significant the same amount of speed up as doubling the core. However, the energy consumption is going to be like this, like 6.4 times, even though I'm just doubling my clock rate. However, if you double the number of cores, you can easily use MDOS law to estimate that, well, maximize in the maximum case, I can still speed up my application by 1.25, even though only 40% of them can be parallelized. However, the energy efficiency is 4 times better than doubling the clock rate. So that's why you see modern processors, they are in favor of double the number of cores instead of double the clock rate. So let me see, what else do I have? Okay, so And the concept of chip multiprocessor, which is the idea of double the clock rate, is like we just double the number of cores, and we still maintain the private cache of each of the core and use the last level cache as the front end of your main memory abstraction. However, there's a big mismatch between the software and the hardware in a way that your software is thinking about it's just a processor core and a shared memory. So it turns out that we consider the shared memory represent the whole shared virtual address space, and each core is a thread. But ignore the fact there are private caches in there. So if you have a private data, if you have a data that has been shared by all of them, and if one of them modifying it, it's impossible for others to see. So you need the hardware support called coherency and consistency to help you manage this data sharing. And in coherency, it means that your data is when all processor needs to pull this data, they will see the same value. That's coherent. And for consistency, it means the order of access. However, consistency is very difficult to maintain. So most of the time, your processor only support coherency, but with very limited support on consistency. So there is a protocol called snooping protocol, and I don't ask you to memorize how it works, but you need to remember that because there is something called snooping protocol to maintain a coherence. So sometimes your data may be invalidated by another thread, even though the other thread is not using that pieces of data that I am using, because remember, cache blocks, they are organized into blocks. So everyone, once you access a block, once you modify a block, it will have to invalidate the whole block, even though it's not on your cache, even though it's on other people's cache. So so when you are accessing another element, even though it was previously in my cache, but because of the coherency, invalidate that data. So it will create another remix to force the cache with the up-to-date data to write back its value so that everyone else can see the same block. So that's how you maintain coherency. However, in the meantime, it also means that you will have false sharing issue. So, and not only that, parallel programming is problematic because you will have this possible scenarios that your thread may not be run deterministically. So sometimes it's going fast, sometimes it's going slower, right? So in this way, you really need some kind so all values, like if you have one variable A and B, and if you have another variable X and Y, it's highly possible that you are going to see 1, 1, 0, 1, and 1, 0. However, that's not just like that, because you have out of order execution. So there's no guarantee that A equal to 1 will be before X equal to B, because it doesn't seem that A equal to 1 and X equal to B, they have data dependencies, right? So there's no data dependencies here, so the reorder will also create such kind of bug. So this is like, sometimes you think, well, the hardware is broken, but in fact, it's just because the software programmer doesn't know this is the nature of the hardware. So you create bugs like this. And to fix this kind of bug, at least you can use fancy instructions to prevent some of the cases to happen. However, it's impossible to maintain the other 3 cases because there is still non-determinism in your program. And most of the time, we don't put like this fancy instructions all the way because it will go to hurt our performance. Finally, we talk about dark silicon problem. It's a case that the DNOT scaling of our transistor or say process technology broken. So DNOT scaling is the fact that we are able to shrink the amount of energy or say power we need per transistor with the advance of process technology. So that when Moore's law grow up the density of your chip, the DNOT scaling will maintain the power consumption to be the same. However, the DNOT scaling is broken. So if you just try to increase the density, then your power consumption will go double. So, but we have limited power supply per computer. So turns out that you can only power on part of the chip and leave the rest of them dark. So that's what we meant by dark silicon problem. So with dark silicon problem, we have a lot of ways to address that. And for example, like NVIDIA's Tensor cores or say ASICs, they are all the remedies of dark silicon problem. All right, so this would give you the highlight of the final. But before we talk about the logistics of the final, I really want to invite all of you to take a group photo with me on Zoom. So what if so if you are willing to turn on your camera right now, it would be great that we can take a photo together. So I will have a chance to like have a group photo with all of you at this point, and yeah, that would be great. And okay, I can also turn on my camera so you can see this is me. Woohoo! Right. All right. So let's take a photo. And try to smile. I will say 1, 2, 3. Again. Okay, one more time. 1, 2, 3. All right. So thanks for that. And now let's talk about the most important thing that you guys are curious, and that's one of the reasons why most of you are still in this class, because this lecture, even though we have already talked about all the materials that are required, because you want to know what's going to be in the final. So here is what's going to be the final. So first of all, logistics. No cheating is allowed. And by cheating, it means that reference online solutions or try to ask your friend, discuss on Piazza, discuss on Discord, or everything, right? So, and make sure you have stable internet connections. And we give you a relatively wide slot, because a lot of you saying that, hey, I am in, some of you saying that I am international students or whatever, or I am working from a different time zone, so I cannot do that, right? So okay, so here's what we give you, right? So we give you a very wide slot, so you can work on any 3-hour slots between this period of time. However, as what we did in the midterm is that we want to make sure I want to make sure that you will completely use out this 3 hours without having time to discuss with your friends. And even though you finish this test, you feel like, yeah, I have done this great amount of jobs. Why should I share my idea with others? So this is how, and another thing to think about that, right? So in terms of a short exam, I prefer a long exam, because there are so many things that we probably won't memorize or won't understand. So instead of just testing you like 5 or 6 questions, but if you miss one, then you miss a lot, right? But I would like to have a long exam. So like if you have a set of if you have a huge amount of questions, and if you miss one, it's just a bit, right? So you won't feel like, miss a question or miss a concept is a big thing. So that's why we have such a long exam for you, because I think it's in overall help us to help you and help us, right? So here's the sample final. So as I said, we have 20 multiple choice questions. We have okay, Nick, question?
I remember last lecture you said we're not going to use a
lockdown browser, right? So that's why we make the final super long.
Oh, is it how do we do it? We just do it?
You just do it. You just go to Canvas and you will find out.
Oh, okay, perfect.
All right. And thank you. And just go to Canvas, and final is right there after tomorrow, 8 a.m. And sample final looks like this. So first of all, we have 20 multiple choice questions. We have free answer questions. We also have 10 essay style questions, which I want to spend some time talking about. And well, multiple choice questions, you are very familiar with them. And don't forget to go through those multiple choice questions that you have experienced prior to the midterm. And so that's multiple choice questions you should be very familiar with about. And for free answer questions, we say we have 3 sets, right? So this is one, like what's the overall cache miss rate of a pieces of a code, and how many cache misses are conflict misses? Can you rewrite a code to eliminate all the cache misses? And like we are going to combine cache and performance. So like saying that I have 80% of the LU instructions, 20% of them are low store instructions, then what's the average CPI, right? And thinking about if within this, what if I make it like 80% of, 60% of LU, 20% of range, right? So what's the average CPI? And then we talk a lot about like out of order scheduling. So and the spirit of out of order scheduling is the data dependency graph. So can you draw a data dependency graph? And if you have a pipeline processor, can you draw the pipeline diagram? And if you have a superscalar processor with 2 issue with unlimited physical register and fetch width as 4, and 2 cycles for integer, 3 cycles for memory instruction, false dependency, how many cycles it takes to issue all instructions, you should be able to find the answers on the slides. Okay, Harry's question.
So whenever we're drawing something like a pipe diagram or data dependency graph, do we have to, is it possible for us to do it on paper, take a photo and upload that to Canvas, or is that all on Canvas?
Okay, so the TA is also here. Boya, what do you think?
As long as it's, I can read it, I think it's fine. But make sure the resolution is high enough, because when I grade some of your homework, a few of you take really bad quality photos, and it's very difficult for me to do the grading if your photo looks like that.
All right, thank you.
All right, thanks, Boya. And yeah, so we have, so Boya will be responsible for grading those free answer questions. So if you can like help her identifying what are you writing, then it will help us to reduce the confusion in grading, right? Okay, so now another type of question, like, okay, we just mentioned, right, for this piece of code, like CD outperform A and B, right? With what architectural support could this be happen, right? Like, or on the other hand, if you don't have that architectural support, will they still be outperforming A and B, right? Okay, another thing, like, okay, what makes adding a sort more efficient, right? What architectural support, right? Make that happen, right? So as a programmer right now, you have to know if I'm working on a processor with this, and this is reasonable to do. However, if I don't have those things, it's unreasonable to do. Again, this question we asked in the last lecture. If you don't remember what Byron and maybe Harris or somebody else, right? They're good discussion. Go back and look at our YouTube. You can probably find some hints there, right? And okay, so essay style question. I think there's a total of 10. And I do list 10 here, so they are important, right? So like, what's SMT and what they solve, and what's the pros and cons of SMT? What's CMP, chip multiprocessor, and why we use CMP now more often now, and what's the limitation of it, and what's coherence miss, when will it appear, and why do we still need dynamic scheduling if we already have compiler optimization? What compiler optimizations can do, what hardware can do, and what hardware cannot do, what compiler cannot do, right? So those are the stuff that we are asking you to think about. And what are the false dependencies, and how can we remove false dependency? And so those are the easy ones. And here are the more difficult ones, right? So we said MDOS law has its own implication on parallelism. So as a software programmer, what did you learn? And what is dark silicon? We just mentioned, right? So if in the future you are designing a new system, how are you going to address the dark silicon issue? And if we have out-of-order pipeline that is highly optimized, as I said, right now, the Intel processor, they have the front end as an x86, but inside the processor is still a pipeline RISC-like processor. Is instruction set architecture still something important? In the last lecture, we talked about volatile, and previously we talked about inline. What are these two keywords in C programming language used for, and why we need them? And why don't we add them all the time? What are the pros and cons of that? And we also talk about speculative execution. We also talk about auto execution. But as a programmer, if you don't know the fact that we have these two things playing in your processor, can you potentially create buggy code? So these are the questions that I am encouraging you guys to think before you take the final. All right. So any other question? Okay, I have Byron, you have a question.
Yeah, when will the assignment 5 solution be out?
I think will be right after the deadline.
Okay, cool.
So wake up earlier, or maybe you can ask the TA during her discussion session, because I mean, even though the solution of assignment 5 is ready, we are not going to give you exactly the same question as assignment 5, right? So it's more important about the concept than the exact correctness of the assignment 5, right? So if you have some misunderstanding that you might have, just as the discussion session. Oh yeah, one more thing, I will have an additional office hour tonight on Google Hangout because I cannot use 2 Zoom sessions in parallel. Okay, Nicole, question.
Just a quick question. Are you gonna post the final slides on your website?
As usual, it will be on the website after the lecture, but give me an hour because I need some time to, drink water, upload it, modify the website, right?
Okay,
but as usual, it will be immediately after, it will be within an hour, I would say. Okay.
Thank you.
Other questions? All right, if not other questions, then again, if you haven't done your survey, go ahead and do it, and it counted as a full credit assignment, and that will be your last chances of boost up your performance. And an additional office hour, you can find information on Piazza, and it's going to be on Google Hangout. Don't use Zoom, and because Zoom has a stupid limitation that if I am the host of 2 sessions, one of them will be terminated. So if I try to launch my office hour, then Boron's CSE141L office hour has to be terminated. So that's not a lot of you would like to see. So so that's why we use Google Hangout. And the link I think is already posted on Piazza. So I will, if you have a question, I will see you tonight at 8 p.m. And that's the last period of time that I can make up for office hour. And you can see that this is that late. So it means like how packed my schedule is to squeeze this time, right? So try to get ready, and it's not going to be a full lecture like this. So prepare your questions. So so we can do the office hour efficiently and get everyone's answer ready. And it's a better of an idea. Like if you plan to attend the office hour, everyone shows up at the same time, and everyone can listen to other people's question in the meantime, so we don't repeat the same question many times, so that we can answer as many questions as possible in a class. Okay, other than that, it's very great to have you guys in the class, and I hope you all have a great summer, and hopefully everything would go smoothly tomorrow, and good luck on your final. And at some point, maybe we will meet somewhere in San Diego or in Southern California or somewhere in the world. And like after this lecture, after this class, I hope to be friends with you. So definitely stay in touch, keep connected. Other than that, thanks all of you for cooperating in this class. I know it's especially tough being an online class, but you guys did an amazing job, and hope to see you one day. Thanks a lot, and good luck on your final.